We are ready for our next talk. And for this one, I'd like to bring on Aayush to tell you about Proteus and ZK email. So please give Aayush a big round of applause.
Cool, thank you. So one thing I wanted to do is slightly reconceive how we see the value of cryptography and defensive cryptographic technology in an age where you have really strong and powerful AI systems. A lot of people have decided, are there ways that these technologies get worse, or are they still important? And I think there's a lot of ways to actually see the cryptographic tech that we're building, including blockchains, and realize that they've become more important in an age of AI, not less. So the way I'm going to go through this is I'm going to talk about briefly, like, what is the motivation for these problems that we're solving? What are some ways people are currently thinking about it? Why are these different tools that we think of so important, and how do you combine them? And then what do we end up with at the end? Okay, so one motivation around where you might think like AI problems and cryptography intersect is provenance. So you see an image online, you want to know exactly where it came from. And not only that, you want to know exactly where it came from extremely fast. The information obviously spreads way too fast, even faster than community nodes, which often settles, between 10 minutes and an hour after content is posted, which is often too late. So you want to know within a few seconds, where did this content come from? The one interesting thing about this problem is that almost everyone is aligned. Lawmakers, government, standards bodies, they all want an answer now. And this is like quite rare to see. It only really happens when, catastrophic things are happening and people need to take action. But this is a nice opportunity where we can say, hey, if cryptography can be useful here, it's actually extremely fast-tracked to adoption. So what are people currently doing to try to solve this? One idea is watermarking. You might have heard of this. The idea is, you take some data saying, oh, this image came from this source, and you embed it into the image in like an imperceptible change to the pixels. And that's kind of like what a watermark is, or like steganography. The problem is it's extremely bad. If you like embed watermark data into an image and you take a screenshot of that image and then you repost that somewhere else, most of the time that watermark is completely removed. If you take a picture of it with your phone, which is the one on the right, like it's totally over. In reality, you can robustly encode about 1 bit, which makes this super adversarial prone. I can just randomly edit an image until that bit changes and then it's gone. Some companies have tried to do like bigger things, like Google tried to make this better watermark called synth-ID, but as we know in cryptography, closed source algorithms are not useful. If it can't be audited, if it can't be looked at, it's not helpful. So, okay, watermarking, nice in theory, but breaks in practice. Okay, what if we used signatures instead? We've seen from a lot of the work that we've already done that signatures are really, really interesting and really important. Why? Well, signatures give you exact provenance of who created it, because you need a private key to create that signature. And once you have a signature, you can layer all sorts of interesting ZK, FHE, et cetera, tech on top of it and get privacy, even if you didn't have it originally. So, some examples are, if you've heard of ZK email before, you can prove that you got some data in your email and that you're now going to use it to, maybe train an AI or maybe show that it's validly generated, or it was generated by a human or a company or a certain kind of process. Another interesting idea is, one thing that a lot of models do these days is they only train on data before 2022, because after 2022, there's too much contamination from, LLM slop online. So, okay, what do? You want to prove you took some human-like actions before that came out, so you're probably a human, or you wrote some information before that happened, so it was likely human-written. And so you can get really interesting provenance on all of that data. I think you'll hear from Self today. You can also do this with passports, where, because passports are signed by the government, you can say, hey, I am over 18, or I am from this country, or I'm not from this country, or I'm not on this OFAC list. And that's quite interesting, because now you get information about yourself as a person in an age where almost any document can be forged, but not the digital signature using this technology. One other important thing is you can prove you took a picture on your iPhone, because as long as your iPhone's not jailbroken, there's technology called Apatest that creates a digital signature of the entire transcript of your app execution on your phone. Then you can prove, yeah, call the camera API, call the location API, this is what it returns. And as long as the phone's not jailbroken, app test will be robust. So, one could imagine technology like ZK email, in which you take an email, you prove the digital signature is valid, and now you can add privacy on top of it. And one very basic example that we've seen with this is, okay, you take an email, you redact the information, you prove, hey, I'm not going to tell you who I am, but here's a document I got from this person. How does this work? You may have seen this before already, but the high-level idea is because emails are signed with this RSA signature of a SHA-256 of all the data in this DKIM signature protocol, you can automatically wrap this inside of a ZK proof and then selectively reveal only the things you want to via more interesting ZK primitives like ZK substrings or ZK regex. Now, it's quite interesting because these proofs are more relevant, not less, in an age where we really care about verifying you took certain action in the real world when any receipt can be faked and the data being authentic. And here's a bunch of examples that people have created with our registry. You can prove you signed a document and both counterparties are in fact who they claim to be. Specifically that the document wasn't forged by some third party who faked a signature. You can prove you actually took a flight or you are kind of at least purchased an expensive flight. So it's becomes very expensive to Sybil attack this kind of system. You can prove you're part of some organization, some Slack workspace, some Discord, whatever, because as long as you get an email confirmation, you can verify that directly without any trusted party in the middle. You can prove you exported your data correctly. This is really nice because if people want to retrain on that data, you need provenance of, hey, this came from here, and I can tell you that that person signed that data. You can prove, even you exported your AI data, and that can be valuable because then you can say, okay, this data was generated by AI. We know what it looks like. You can prove, you have action in the past, like, oh, I merged this GitHub issue. That's quite interesting. We've already seen things in crypto where people are using this kind of thing to say, okay, now I can build something like a, incentivization protocol on top of GitHub, where you claim money just by proving you merged the issue. And you can prove you KYC directly in the past and then reuse that anywhere else you want. It's quite cool because this stuff works. People have done over 5,000 proofs of this in production. Various versions of these, including Uber orders, Amazon orders, all sorts of weird things. And we've shown that it's very easy for users to just hit sign in with Google, make all these proofs that they want to, and it's a very intuitive user flow. But what have we learned from all this? Okay, digital signatures are really important. They give you provenance, and as long as you have a signature, you can add privacy where you want on top of it. Okay, so let's go back to our original problem that we wanted to solve, which was deepfakes. We want to know where a deepfake came from. There was one algorithm proposed a few years ago that has some flaws that we'll talk about, but it is a good first step. So the idea was they would take an image, they would hash it, and then they would sign it. Kind of exactly what you see in the very naive application of signatures to provenance for images. And the idea is, if the image changes a little bit, the hash won't match, and therefore the signature won't match. There's a lot of problems with this. The main problem being that metadata, which is the signature, is stored in the metadata of the image itself. The problem is you lose this metadata every time you share the image. If you screenshot the image, metadata gone. If you share the image on Twitter, metadata gone. You send it to your parents on WhatsApp, metadata gone. Post it on TikTok as part of a video, metadata gone. So the problem is, because this is stored in image metadata, all the way that you see people sharing content today don't work. Like you lose this provenance immediately, and there's no way to get it back. So okay, this is a nice idea in theory, doesn't really work in practice. There's also a lot of criticisms, a lot of issues with this. There's lots of weird kinds of fraud. There's lots of, the kind of way that they forge a C2PA signature is that because there's no verifiable timestamp, if you fake the timestamp, you can fake the signature. We already know a great tool to solve this, which is blockchains give you global consensus over time. This is, again, using their weird specific certificate scheme, like X509, is quite hard for people to use and also has various issues. Again, the timing issue, and the fact that it sometimes isn't actually going to be authenticating the media. Funnily enough, the person who posted this, Hacker Factor, had a really funny solution, which is just email the content, you get the DKIM signature and use that for provenance instead. Which is kind of fun because we already know that's a signature that works, that we have proofs of, that we can do things with. Another, this is, again, using their weird specific certificate scheme, like X509, is quite hard for people to use and also has various issues. Again, the timing issue, So okay, let's say you have this signature. Imagine now you wanted to protect it against those transformations. You wanted to protect it against, modification, against compression, against cropping, whatever. One set of work that tried to look into this, I'll explain the pros and cons in a second, is Veritas VimZ, which basically looked at, okay, let's say you have the signature from a camera or an image generator. Now, the idea is every time you edit that image, you're going to create a ZK proof. You can say, okay, I made a grayscale and I cropped it. And you make a ZK proof of those transformations. And then when you post the image online, you post both the signature and the proof everywhere you post that image. Okay, this is like an interesting start, but the problem is I don't think we can be expecting Instagram filters to be adding ZK proofs to their backend anytime soon. And not just that, but this won't work if the image is modified in image editor that doesn't support it, or if the image is turned into part of a video, you won't be able to get provenance. And so this is nice in theory again, but in practice doesn't really work because you can't expect every single image editor in the world to add ZK proofs to their backend. Okay, back to the drawing board. What if instead of signing a hash, like all these solutions advocate, you instead signed a value that was transformation proof from the start? Okay, and this is where kind of this more novel Proteus system comes in. The idea is you can try to create robust provenance via digital signatures, which we know work, but have not been totally used well in practice. Perceptual hashing, which is a non-cryptographic type of hash that ideally keeps the image content quite similar, and privacy technology layered on top of it, ZK proofs, MPC-FHE, etc. Okay, so maybe because this is one of the cruxes of the problem, what exactly is a perceptual hash? The idea is that you want some representation of the image that is transformation proof. If you imagine more transformation happening as you go towards the right and less perceptual similarity to the original image as you go down, the problem is as you modify the image more, post it more, as the image spreads more, the actual content of the image changes more from the original perceptual value. It gets compressed, it gets resized, whatever. And you kind of want some representation of the image that is the same along every point on these curves. Okay, so here are some very basic, very old examples, but we'll give you an idea of what such a value could look like. On the left side, you have the palette of an image. It's quite nice. You just say, what are the main colors in the image? Even if I rotate the image, crop the image, the palette stays the same. If I compress the image, the palette stays the same. This is quite nice. This already gets you some of the properties you want, but isn't perfect because if I apply a filter on top of it, okay, this palette is now completely useless. Okay, the image on the right, try to have a different kind of perceptual hash, which is, hey, what if we took the image and we downscaled it to 8x8 grayscale, and then we quantize the grayscale values. Okay, this is nice. This is robust to filters at least, but isn't robust to rotation or cropping or things like that. Okay, so Apple proposed like an AI-based perceptual hashing system. Again, this is not like a cryptographic hash. This is just like some representation of the image. Very simple. You just get the features from the image with a neural network, and you threshold it and make it into a binary hash. This is okay, but there's lots of attacks. These have the same neural hash. You can find neural hashes manually. There's lots of people who have broken these kinds of hashes. But if you look at the actual performance on transformations, it's much better than we were seeing before. With C2PA, any transformation, all these numbers are 0. Here, you can consider this number to be how similar your new perceptual hash is to the old perceptual hash, and at least you're pretty close in most cases with an AI-based perceptual hash. Although obviously there are still problems. So the idea was, what if we took this kind of architecture and we made it better? We made the feature extractor better, more robust. We added adversarial training into the whole mix, and we added an extra PCA step to make the feature extraction easier, and that's where our algorithm DINO hash came in. Okay, so I'll explain a little bit more about the results towards the end, but just so we can construct the full picture of the system in our head, imagine we have this perceptual hash. Now how do you build a robust provenance system on top of this? Okay, so you can say the image generator, which can be either OpenAI or a camera or whatever your favorite image generator is going to generate some image. Now they're going to sign the DINO hash of that image. The signature can then get posted to any DA layer, which is going to keep the timestamp, global consensus over the timestamp of that image, the time that that image was signed. And then, so the user on the left generates the image. Now they're going to share it on social media. So they're going to, put it. Social media is going to compress it. It's going to get cropped or whatever. And now the person on the right wants to learn, where did this image come from? They see the image on social media. Where did it come from? This could be a user. This could be a social media platform like Twitter. This could be whoever wants to establish the provenance. All they do is they now query, hey, I see this DINO hash online. Who signed the closest DINO hash to this value I see? And you can say, hey, we saw that OpenAI signed a DINO hash that was 80% similar to your current one. This is decent, but not perfect because it's missing privacy. The main problem is that you want to keep all parts of all the images private. This means that you really, really care that nobody can reconstruct the text prompt that was used to generate an image because that's where a user's personal information is. You really don't want to reveal that PII. And these AI generation models are so scared that they're even too scared to release the hash permanently, like the perceptual hash permanently. Because the perceptual hash is not a cryptographic hash. You can reverse it with an advanced enough model to get the original image. Usually a blurred version of it, but still it's enough to encode the semantic content of the image. And in fact, many of these AI image generators will delete the images after 60 to 90 days to keep this privacy. Okay, so how do you now build privacy into the system in a way that's compatible with those needs? The idea is that you can use MPC or MPC FHE to create a database of these perceptual hashes and then do the lookup in a completely private way on both sides. One example of a team that did this was WorldCoin built exactly this kind of almost perceptual hash check with an MPC database in the back and could do about like 4 billion matches per second. Admittedly, they have a lot of GPUs, but this is like pretty good. And so, okay, what is the new change to our system? The idea is we're going to take our entire hashing architecture, but instead of doing the matching in plain text on the DINO hashes, you're going to do it inside either an MPC database or an MPFHE database if FHE becomes fast enough. The idea now is that all these content producing organizations contribute a machine to this kind of organization of machines that is going to do this lookup, and they're going to check just the operation, what is the closest value in the perceptual hash space that's been uploaded, and if there is a closest value, who signed it. So now you can see when the user on the right queries, they're going to send their homomorphically encrypted value into the server. That server is going to do a very concrete operation that no machine can learn what thing was queried and which images were found. And they're just going to return who created the provenance of that image and how close was that image. Okay, now one problem here is that you can't expect the system to exist overnight. There's like this cold start problem where you need people to sign up for the system. You need people to be signing images. You need people to be interpreting them in the right way. So you kind of want some like fail-safe until you can get adoption here. And that is you can have a very simple AI detection model that just says, is this image AI or is it not? And that's kind of like the backup fail-safe. If you don't see any signature, you have like some sort of backup say, okay, actually we're going to do this instead. Okay, so what do our results look like? So on the right side, you can see in the yellow line is Facebook's chosen stable signature. In the middle is Apple's neural hash, which is like the blue line. And green on the left is the DINO hash that we trained. So the idea is that the way to interpret this graph is the more to the up and to the left you are, the better it is, because that means the more images you're able to correctly identify. It is like the ROC curve, but yeah, the idea is that because the bottom is in orders of magnitude, we're doing already orders of magnitude better than many of these existing solutions for the same kind of threshold accuracy level. The other big issue is adversarial training. It's very easy to adversarial attack existing perceptual hashes, and to our knowledge, no one has ever adversarially trained a perceptual hash model in the past. We did, and it turns out that if you edit an image by small amount, like 4 out of 255 pixels or 8 out of 255 pixels, at most, you can change a perceptual hash by 40% of the bits in the worst adversarial attack. So no matter what, as long as the image looks perceptually similar, 60% of the bits will be retained. And that's like a pretty different result from what we've seen in the past. As you can tell, like nobody else considers this kind of attack, which I think is very important in the real world. People are going to try to look at your system and modify a fake image to pretend to have the provenance of a real image. So this is like, I think, a must-have for any deployed system. At the bottom, we have like the backup AI training model that I mentioned of just like, hey, here's a simple classifier. Can you detect real images in the wild properly? There's a nice new data set called SynthBuster. And if you run, very simple AI detection model trained with just the kind of the latest SVMs, you can get like basically state-of-the-art accuracy across detection on like all existing kind of real-world generated images. Okay, so the idea is you can create robust provenance by taking lessons we've learned about how important digital signatures are, using perceptual hashing to get around modification, and then adding MPC or FHE for privacy. And of course, you have a backup as you deploy the system into the wild. And maybe the main takeaway is I think like Ethereum and these technologies that we built can be used for much broader things than we've kind of considered in the past. And there's lots of interesting ways to contribute. Lots of things left to do, red teaming it, making it useful, optimizing the system. If you want to learn more, website that explains more, paper on the left. The work that I do most of the time in ZK email is in the middle, which is very relevant and informed a lot of this work on the that we just presented. And my Twitter is on the right, where you can hear me yap about all this stuff. Cool. Thank you.